I'm Maya. I'm currently in South Africa, and you've heard my introduction. Now, I don't know if my slides are on screen yet. Kimmy, can you hear me? Can you add my slides on screen? Ah, fantastic. Right. So my topic is imperative, declarative, object-oriented, functional, four of a Kotlin kind. And you've already got my introduction. And if you need to find me on Twitter, you'll find my Twitter handle at the bottom of the slides. Okay, let's see if I can get this to click. Sorry for the technical glitches. Right, so let me just give you a disclaimer. So why am I doing this talk? So I come from an engineering background, not from a computer science background, but I've been a mobile engineer a long time. And often I meet people and then they say, oh, you've got to do it in a functional way, or that's very object-oriented, or that's very imperative. You should be doing it in a more functional way. Various times people have used these terms, or that's very declarative. They'll say Jetpack Compose, that's extremely declarative. That's very good. Or you're coding things and not in a very declarative way. And it was always a bit of a mystery. I had an intuitive feel for what these terms meant, but I didn't understand exactly what they were. And so what I decided to do was I decided to do some research to understand exactly what these terms mean and how they fit together. The other thing to mention is if you just look at the slide, you'll see what are the languages that I have experience in. So I come from a background of BASIC and Pascal and machine language, which are very imperative languages. I did a lot of C and C++, a little bit of Bash, a smattering of Python, Java, tons of Java, briefly dabbled with Scala. Then lastly, I've been spending a lot of time in Kotlin, and Kotlin is the language that I love to use at the moment. So what you'll see there is I haven't really had a lot of experience in functional programming languages at all. So that's just to set the scene. That's the background of what my language experience is up to now. So let's take the first topic. Let's take imperative code. So according to the Wikipedia, the definition of imperative code is that it consists mostly of a series of commands. And you can see just a sample of some imperative code on the side here. Let me just see if I can get my laser pointer sorted out. Right. So the thing you see in imperative code often is you might see for loops. You might see some other looping structure like that. You'll see some ifs, some conditionals, and you'll see some places where some variables get set and some variables get read. So those are like very clear signals of an imperative language style. So what I'm going to do in this talk, what you'll see me do is I'm building up like a visual language to try and picture what these languages, what their shape is, so that when you read them, and when you see a piece of code, that you'll understand, you can get a feel for what the language paradigm is just from visually looking at it and seeing how things are put together. And an imperative language, let's say these white lines, they're statements. And this blue cloud, that would be like the state of the program or the memory. And typically what you would see in imperative code, you'd see some things, statements happening. Then you would see some value being set inside the state or the blue cloud, the big blue cloud. And then at another point, you might be reading out of the blue cloud. There might be some other conditional like that, which could cause something to loop and get something to jump back. So that's what it looks like for imperative code. Now, I'm not talking about side effects. I'm talking about how the structure of the code is built up. But anybody who's written more than 15 lines of imperative code quickly finds out that their code ends up looking like this. So you'll recognize this. This is like a huge, big spaghetti mess thing. It's like the state gets changed. It's the global state here. It gets read in lots of different places. Maybe it gets written in lots of different places. There are loops, and that depends on the state, and then it jumps back and forth. So this is a problem, and this is the kind of thing that when you're coding, this is what you're trying to solve, because code that looks like this is extremely difficult to understand. Because what are we doing, humans? When we try and debug this, we literally play back what's happening here in our brains, in our head. And humans have only got 4 registers or 4 pieces of working memory. Computers are very good with memory. They have lots of memory, and a computer can keep track of what's going on here and how things change. But humans have only got 4 working slots. Maybe it's not 4. There's research in the 50s that say we have working memory 5 plus minus 2, which means it's between 7 and 3. But for me, it feels like 3 or 4. And how you can understand how that works is that if you try and tell someone your phone number, then you might say something like 021 556 6655. And what you're doing there is you're taking all of those numbers and you're grouping them together so that they fit into these memory registers. So that is a neurological thing called chunking. And so what you're trying to do is you're trying to make sense of the chaos. So what you need to do, what all of these language paradigms do, is they're trying to cut through complexity, because if the programs become big, there must be a way to group things together so that if you see one word, that you understand what that is, so that you can read the code and so that you can understand it and so that you can fit more code into your mind. So if you're an imperative coder, the first thing that you might do, because humans are really, really good at pattern matching, you might look at the code and you might see some duplicates like this. You might see some lines of code being repeated. And then the first instinct in imperative code is to pull these out into functions, and that's called procedural imperative code. Now, if you pull a piece of code out into a function like this, what you could do is you could do it one of two ways. You could either from this function write straight into the memory and read back out of the memory, or you can pass parameters into the function and pull the parameter and return the parameters out of the function. Now, if you do that, if you don't allow anything inside this function to access the global memory, this is what's called a pure function. We'll get back later to the pure function because you use that in functional code as well. But what you can see here is you can write pure functions even if you're coding in procedural imperative code. Enter Kotlin. So now I love Kotlin. Kotlin is my favorite language. I think since all time, Kotlin is my favorite language. And I was interested in how does Kotlin help us? How does Kotlin help us with all of these language paradigms to make sense of the chaos, to cut through the chaos, but how does Kotlin support the different paradigms of language? Now, I don't know what the audience level is and how much experience you have and who's got some functional experience, but I'm just going to go quickly past the basic Kotlin pieces, and we probably won't stay there long. And if you need more information about the basics, if you're a beginner, then you can always ask me on Twitter. So for imperative code, you obviously need to be able to write and read inside the blue cloud. And what the thing that Kotlin does to support this really well, it has this concept of mutability. So this variable here, pi, that one can't change. This one can change. You can see you can change things here. The other thing that Kotlin has to support this kind of coding is the concept of nullability. So this name variable here is of type string that's nullable, and this is actually a different type. Something, if it were type string, that means you can set it to null. Then the other thing we saw in that sample code was some ifs. So you can get there various different kinds of conditional things that can happen in Kotlin. We've got an if statement here. Interesting to note here, this is not a statement, it's an expression. And it means we can set the answer to this into this variable. We'll see some more of this when we get to the functional piece. And then the when, which is another form, which is like a multiple branch. Loops. Kotlin has for loops. You can see you can do different looping structures here. Kotlin has a while loop. Kotlin has a do while. The thing that's interesting about the do while for me is that if you read this code like this, you see this y over here, which is in the condition. And because the variable was declared here, I would expect the scoping to not allow you to see y here. But because it's part of the do while, that's the part of the syntax, you can actually see this variable over here. And the other thing you need for procedural imperative code is you need to have a top-level function. So you need to be able to, anywhere in your code, make a function so that you can call it like this. And here you can see this is a pure function. The other thing that we saw with imperative code was those jumps. So there was just a way of coming from one place to another place in the code. Kotlin allows this only inside loops, and there are various different ways of doing this. You can either continue the loop, break out of the loop, or break out of a loop with a label like that. So that's a little bit like a goto, except it's more controlled in that you've got a label and that you can only do it out of loops. The other thing that Kotlin has is exceptions. Now, exceptions are something that languages have had for a long time. It's not only something in object orientation, but I consider this exception to be similar to a loop. I see it like a loop because when it gets thrown, if you don't catch it, it's going to jump right up to the top level where something catches it, or it's going to jump right out of the code. So by going throw exception, you're basically forcing the program to jump somewhere. you can call it, you can throw an exception inside a loop, and it's going to make you jump straight out of where you are. So I categorize this as part of jumps. So the pros and the cons. For me, imperative code is easy to grasp. People learn imperative code first, and people have like especially if you've used machine language or some of the more lower level languages, it feels easy to grasp. But the minute the code gets big, you have complexity, and it's difficult to follow and it's difficult to track what's going on. Ryan, have you got a question, Ryan? Oh, no. Okay. The other con about imperative code is that the state, which is that big blue cloud that I showed you, and the behavior, it's mixed up. You get a mix of the state and the behavior, or in between each other. There's no separation. All of it happens at the same time, which is very prone to the complexity that we see. Okay, let's move quicker on to declarative. So these computer science people, they're quite interesting. They like defining things as if they're not the other thing. So declarative is a non-imperative style of programming in which programs describe their desired results without explicitly listing the commands or steps that must be performed. And if you want to see just a sample of what that could look like, this is Jetpack Compose. There's some state coming in here. This is a function, and we're not saying how the card gets drawn. We're just saying we want, depending on what the state is, we want the card to look like. If it's face up, then it must show the suit. And if it is face down, then it must show the back of the card. So that's just an idea of how it would look like. And what would the picture of this look like? So what you have typically here, if you're thinking about something like HTML and JavaScript, or if you're thinking about something like XML views and code in Android, or if you're thinking about something like views in Compose and behavior that's sitting in the view model, there's a split. There's some piece like the XML views or the Jetpack Compose, which says, I want a picture, I want an edit text, I want a button. And then separate to that, which you've got a hook to that, is the state has to come into that declarative piece of code. And the behavior, like if you click the button, it goes back. So maybe you're calling back into the view model. There's a lambda that you call to get the behavior. So what you're seeing is here that what people have done to break up the complexity is they split it. The blue cloud and the state is still there. The behavior is still there. It's just split from the place where you say what you want the UI to look like. And what this means is that to be able to do this, you need some other framework here to describe the declarative part. So typically with declarative systems, you need to understand the XML of the views. So if people are saying, say, oh, Jetpack Compose is more declarative, I would argue that the view system is declarative as well, because you're declaring what views are need to be inflated in the XML system. Now, for something completely different. So I know computer languages come from the time of Ada Lovelace, but I was thinking about this. This is a different way of thinking about things, declarative or imperative. And I would argue that people have been thinking in declarative and imperative ways of working since a long, long time ago. I mean, the history of knitting is extremely old, and writing knitting patterns is much like writing code. It's an algorithm of sorts. You want to have certain stitches that happen that produce something, but the algorithm needs to be interpreted by someone else. And so if you look at knitting patterns, you'll see here this kind of knitting pattern. It's from 18 something. This is an imperative language. It's got the actual steps. You need to seam together, you need to pin, slip, and you need to repeat. There's your loop, and the number of stitches would work like the state. So this is a very imperative way of looking. But knitting patterns and crochet patterns from the beginning of when the patterns have started been writing, they had this format as well, which is just a diagram which says that these black squares have got a certain stitch and the white squares have got a different stitch. How the stitch is done is not said in this pattern. This just says when I'm finished, the bottom of this piece of fabric must look like this. So this is the declarative system, which has another format, another layer that you need to know. You need to learn that this stitch you do in a certain way and the white stitch you do in a different way. And so what kind of things in Kotlin do you need for a declarative language? You need to be able to pass in a function as a parameter, because otherwise you can't do the behavior. So like this, there's a transform here. This is a lambda. And this way, syntax over here says that this is a function that takes in an int and returns an int. And this is how you would use it. You would use it like this. Now, the thing that's interesting about Kotlin is that if you have it like this, here with this round bracket and this round bracket, and the last parameter is a function, you don't need these blue brackets. You can leave those out, and that's one of the ways that Kotlin supports passing in a function as a parameter. The other thing that's useful for a declarative language is to be able to have infix functions and infix operators. So if you define an extension function like this, and this is useful for when you're trying to build up a declarative system, or if you want to write a DSL, which is another way, which is also a declarative way to set some code up. So let's build a quick DSL just to see if we can build up a declarative language framework just quickly on top of the Kotlin examples that we've been using so far. So here I've got an enum, which is a suit. I've got this data class, which is a card. We're going to come to the object-oriented way of working in a minute. And it's got two variables in here. It's got suit and it's got points. Now, to set up this DSL, what we're going to do is we create a new function called card. We pass in a function, but we do this interesting thing. We say that this function, this init function, is running. This is an extension function that runs on card. And what does that allow us to do? That allows us to access certain things inside card from inside this init function. And then inside this card function, here, we create a new card. We can now call this init function on this card that we created, and we're returning the card. So this is just the scaffolding underneath for us. Now we're writing this DSL to be able to use something, create a card in a declarative way. Now here you can see I'm using, this is a function. It doesn't look like it. It might look a bit like HTML, but this is the function being called. And here we're passing in the lambda that can only run on a card. And here this suit is visible to us. If you write it out in full, you would say this.suit, and the points is visible to us, this.points. And so this is a declarative way of setting up this card. Now, if you've been reading your Gradle build files, you might have seen a syntax that looks like this. And in fact, the Gradle syntax in the Gradle build files is a DSL that's there for us to be able to configure our builds. And so if you look at another example of a declarative example, this is inside the Gradle build file. This is just a function that takes in a lambda that is run on an object which has a compile SDK, which has a default config. This default config is another function that runs. And so over here, you would have had this dot version code. So this is what's happening inside something which is your build KTS file. It's just a DSL, which is built in exactly the same way that I showed on the previous slides. Some pros and cons. It's easier to reason separately about state and behavior if you split things up. If you say the state and behavior is here, and we're just reasoning about the state and behavior, we're not thinking about what the UI looks like. So for instance, we're reasoning about the state inside the view model. We're not thinking about how the actual compose elements look like or how the XML looks like. And we can make rules. We can say that if you want state to flow, you can for instance, you can say unidirectional data flow, which says that inside the declarative piece, you're not allowed to change the state. The state only gets changed inside, say, the view model, and it can only be changed by the behavior. And it can be less code. So if you look at the way we declared the card in the previous example, you end up, once you've built that DSL, you end up with code that is smaller and is more compact and less to read. The flip side of it is this red arrow that you see here, is that there's always a learning curve. You need to understand. So you either need to understand what's happening in the Gradle file, or you need to understand how to connect the XML in the view system, or you need to understand the different composables that you create in your system to make your declarative UI. The other thing is you also need, when you're debugging, for instance, you need to look in two places. So if you're debugging the state in the code, you might look in the one place where the state in the code is. But if you're debugging the UI, you might be looking, say, in the preview for Jetpack Compose. So there's this concept of that you're looking in two different places. It's easier now with Jetpack Compose, but even with a view system, you would be debugging something in XML, and then you would go back into your fragment or activity to see how that was connected through. And there will always be some other domain-specific framework that you have to learn to be able to understand how the DSLs work. Now I'm going to go quickly over object-oriented because we all are very used to it. The definition encapsulates the state and the operations inside objects that support inheritance and polymorphism. A quick example, we've already seen our card object from before. There's a suit card. We've got some state over here that's being kept in these vowels, and there's some behavior that you can have that in the methods for this object. So how does this look? So here I've got, say, a parent object. This child object inherits from this parent object. But can you see the state is living here now? It's like we chopped the big blue global cloud into multiple little pieces, and those pieces are sitting inside the objects now. And the big line of statements, they're being chopped up. So it's just a way to separate that big spaghetti mess into something we can understand. And what this means here is that this object over here, it can see the blue cloud here, but this object over here can't see this blue cloud here. And so it's a way that if we're in this object, we know you don't have to worry about this piece of the state because it cannot see it. It's a kind of scoping. So it's a way to make the complexity more understandable, but by splitting things up and putting the state and the behavior together. So again, quickly some code. There's a class. In Kotlin, there's a data class, which is really useful because it automatically generates some code for some of the things that you might need in a class, like a hash function and an equal function. And it automatically has getters and setters. That's part of the compiler does that for you. Here we have an enum class, and you can have interfaces. And this is what the inheritance would look like. I'm not going into the detail, but this is just this picture in code. And this is how you would create these objects. What's interesting as well that Kotlin does, which is really useful, is that it has this concept of default parameters and named parameters. So for instance, this Joker has all of its suit and its face value set, and you don't need to have the parameters because over here, oh, do I not have the Joker? Okay, so the default parameters is another way that in the constructor that's really useful for Kotlin. And it helps us because we can get away with not using the builder pattern. It's got generics. The cool thing about generics is you can use it as a class, as part of the state of the class. You can also have a function return a generic, and you can write an extension function on a generic. Now, I mentioned about patterns earlier, about that you don't need the builder pattern because you can have name parameters. There's some of the object-oriented patterns. Now, the patterns, the gang of 4 patterns, you might have met some patterns. Those patterns are typically created when you're coding in object-oriented languages. There are a lot of supplementary patterns of ways to hook objects together that the industry has decided on and that's been written. Now, some of these patterns have actually been coded into the Kotlin language so that you don't need to code the patterns by yourself. If you were in Java, you might need to code up a delegate pattern or code up a builder pattern, but it's part of the language. So for instance, an example would be the delegate. So if you can use this, you can set up a delegate like this and the language supports it. So you might have an interface that says something can print. And if you've got this printer and the printer can print, it can override this print function. And then when you use it like this, you might have some or other class that couldn't print before. But if you pass it in something that can print, you can use this by keyword, and then it will automatically route all of the print calls through to the print class that you passed in. So that is an example of an object-oriented pattern that's built into the Kotlin language. Another place where you see this is this lazy instantiation. So if you use here, this is delegate, and what it's going to do here is it's only going to run this lambda the first time this value is being accessed. Some quick pros and cons. We humans are used to objects. I mean, I can think of a light switch, and a light switch I can press, and the light switch can be on or off. And so there's an intuitive connection to object-oriented programming. Or if you can think of something like an object on a screen or a graphical something, like a button or an edit text, it's easy to imagine the code and do that grouping inside objects. So to an extent, it's easy to understand. And the state and the behavior is encapsulated. So that's that blue cloud and the lines. That's all together with each object. The con of it is, though, that everything is not an object. So I've seen code bases where you have these string utils or pattern util classes, and that's typically an indication that someone wanted some functionality. They want a whole lot of text conversion functionalities. Typically, those functions are all pure functions. They just take all of the data in, they spit something out, but they're put inside text utils or string util because you were coming from Java and you had to have it inside an object. And then the other indication of when things are not an object is if you see a code base and there are these manager, coordinator types of classes, which don't map clearly to an object. And when their behaviors start getting mixed in between these classes, that's typically an indication of that there's a confusion there. There's a thing you're grouping functionality together, but maybe they don't need to be together because you can't name the object properly. The other thing to know is that if you're making an object, there is some memory usage. When you create the object, it needs more memory to be able to group together the behavior and the parameters and the methods and the state inside the object. And because of that, you might find that you get a performance hit. So a typical place to see that is if you say have a draw loop, and inside your draw loop, you're allocating objects, you're making new objects, you'll find that you'll take a performance hit for that. So now let's move on to functional. I know there were some questions in chat about monads. I'm going to speak about monads shortly. I'm going to see if I can go a bit slow on the functional part because this is the part that most people are probably not that familiar with. So the definition of functional is, in lieu of assignments, use procedure calls to bind variables to values so that referential transparency is preserved. Now, for me as an Android coder, that means almost nothing. I mean, I can pick the words out, but I can't understand exactly what they mean by that. I've got to slide a little bit further on where I try and explain for you what this means. But this is like a really weird definition of functional languages. I think it's easier to understand how functional languages work just by looking at some examples, and we'll do that. So here, this is a function. We've got a function here, score jokers. And what this does is it takes a deck, which is a list of these cards that we've built up, and you can call some chained methods on it. You can filter out the jokers. You can map. You can change the joker cards to just their point values, and then you can add them up. So this is an example of what functional code could look like. And so here's the slide about referential transparency. So I mentioned this function here that we had in the imperative part, which is a pure function, which means that inside this function, you can't access any outside state. Everything that comes into this function that it needs to spit out an answer comes in through parameters. And when it runs, it only has access to the parameters that come in, and it always produces the same answer. So if whatever happens inside here, if it returns 5, no matter what the parameters are, if the parameters stay the same, the answer is still going to be the same. So that's a pure function. Now you need a pure function to be able to do this referential transparency. So for instance, if we had this function which says, give me 5, and no matter what, it takes no parameters and it always returns 5. There it is. There's the function. It always returns 5. Now, if you have a statement like this, x equals give me 5, you can replace it with x equals 5. You can swap out the answer to the place where the function is. So all the places where the function gets called, you can just swap in the answer and your code will not have any bugs. Your code will always work correctly. So that's referential transparency. Referential transparency says if you know what the answer is going to be, you can swap out the function with the answer. And this is a really useful trait. If your code is written like this, it means if you've got some piece of code that's heavy, that does a lot of calculations, the same calculations over and over and over again, and the functions are pure, and you already know ahead of time what the answers are, you can set up a hash map that just returns the answers. And you can do this because of referential transparency. So I've seen people doing this. It's called memoization. I've seen people do this in code. And that's a thing that you can do because of the fact that you're using pure functions. So now let's look at a snippet of code. So say we had some for loops that did something inside here. There's a list. This for loop runs over this list and then does something. Maybe it changes the list or maybe it doesn't change the list. Elsewhere in the code, we have another for loop. It does something else. We have another for loop. It does something else. Now, if you come from an imperative background, if you look at this code and you're trying to split out pieces that you can put into functions, you might be tempted to take the inside of this for loop and split this out into a function. But in a functional way of looking at this code, the pattern that you recognize is not that you can split these pieces into functions. It's that you can split the for loops into functions. And so here you've got a function called map. And what it does is it loops through the list, and it does whatever you let it do inside this lambda. Now, the difference between this and this, here, this for loop has to access this list outside. It gets it from outside. Here, this acts on the list, but it doesn't change the outside list. It just returns a new copy of the list if things are modified. And what it looks like in pictures is like this. You might have some other list at the top. You're calling maybe a filter function, and then maybe you're calling a map function, and then maybe you're calling another thing, say a sum function. And you can chain the calls like that. And then these functions over here, they need to be pure because they just take whatever comes in. That's what they react on. Now, do you remember we had the exception? Now, if you had this code over here, and inside here, you threw an exception, right? Something happens. You do something in the list, something's wrong, you throw an exception. If you're chaining these calls together and you throw an exception in the middle here, it's going to jump right out. It's going to break this code here. And in fact, if you're throwing an exception inside a function like that, that function is no longer pure because something can make it behave differently depending on how things are happening. It's got a side effect. So what people in the functional world did, if they have this situation, so an error could occur here, but what you want to do is the output of the function, you want to be able to say, okay, either there's an answer that came out here, a new list, or there's an exception that happened. So what the people in the functional world did, it's a pattern. They created a pattern, much like you have a pattern in the object-oriented world for delegate. There's a coding pattern that says you're not allowed to throw exceptions in the middle here. What you can do is you can make a new kind of class here that can be either there's an error inside it or there's the answer that you're looking for. And then when this next function gets that function, that return value, it can see there's an error in it or there's an answer in it, and it can respond appropriately. What I've just described to you is the solution to that exception jump problem, but it's also the crux of what a monad is. So for functional programming, there's another slide on monads. I'll explain it in a little more detail further on. But the first thing you need for functional programming languages, obviously you need a top-level function, because otherwise you can't call these functions from anywhere. You need to have functional types and lambdas. We saw this already from the declarative part. So I'm not going to go over this code in detail again, but you need to be able to pass in a function like this transform function. And then there you can see the curly braces. Those round braces are missing over there. And now here's the slide about the monad. Now everybody gets all antsy and panicky about a monad. And I have to admit, so did I. It's like this big word, and then you hit it, and then when you start researching it, you get a mathematical definition. And then it's just like, from then on, it's like, how do I even connect to this? How do I do this? But the crux of it is, it's a software pattern. It's a software pattern that you use to wrap things. An example of a way that you could do this is if you had these functions and they return this box, which is a monad. Inside the box, it could have the answer or it could have the error. This function takes the box. If there's an error, it changes it to be another one of these boxes that can either take a function, can either return the error or the answer. And so it's just a wrapper around the return values here that could be true or false. Or it could be success, the answer, or an error. And for it to be a monad, you need a way to wrap. You need to make this outside class. And you can have something different inside. So you need a way to create this wrapped class. And you need a way to transform it. So for instance, if this function returned strings and this function returned numbers, but both of them could return an error. If there's an error coming from this one, then you need to still be able to return an error here. So you need a way to turn the strings into numbers, but still have it the same wrapping class that can have the answer, and the error in it. And if something has this way to create it and has this way that you can transform it, then it is a monad. Even with the mathematical definitions, then it is a monad. And then what it allows you to do is it allows you to chain functions like that. And then the errors can fall through without needing an exception to jump out of the function. The other concept that people in functional languages often use is the word currying. Now, Kotlin doesn't support currying out of the box. There are libraries that implement it, and currying just says that if you have a function with 2 parameters, you must be able to split it into a function taking the 1 parameter that is a function that you can pass in the second parameter. It's useful in some cases, but in Kotlin, if you need to do it, you can code it up or use a library to do currying. And now let's have another little break. We'll do something completely different. Now, this is a page from a book that talks about the Fibonacci series. The reference of which book it is, it's very old. It's a mathematical book. And you can see here the numbers are Arabic numbers. They were using Arabic numerals, and you can see the Fibonacci series here. And why have I got this here? Because there's another very interesting thing in Kotlin that supports functional code as well. And this is this tailrec keyword. Now, there's a solution to the Fibonacci puzzle that produces this series of numbers. And one of the solutions, there are many solutions to this puzzle, but one of the solutions are where you call, it's a recursive function. You write it for the bottommost values of n, and then from then on, you call it recursively. Here you can see there's the a plus b, which makes the Fibonacci function. Now, if you didn't have this tailrec, this function needs to push its parameters onto the stack, and then it calls itself again and pushes parameters onto the stack and calls itself again and pushes parameters on the stack. And you can do it for a small amount of numbers, but if you do it for big numbers, if this n becomes very, very big, then recursively, because it nests in and every single time it calls itself again and calls itself again and calls itself again, it pushes values onto the stack, it quickly runs out of memory. There is another way to do this, but you can code this up like this, and then you can add this tailrec function, and then the compiler will go and it will unpack that code and make it not be a recursive function anymore at compile time. Now, that sounds like magic. It's only possible if this last call over here is the recursive call. Then only can you use the tailrec. Now, someone in a talk asked me, like, if it can do this, why do you need to say tailrec? Like, why do you need to even do this? Like, why can't you just like leave the tailrec method, the keyword out, and then the compiler must just do it if it can? Now, I was thinking about this, and what I was thinking was that if you wrote a function like this, maybe it's not Fibonacci, maybe it's some bigger, much more complicated function, and you want it to be tailrec because you know it calls like this, but some other developer comes after you and they have to do maintenance on this. If you didn't explicitly write the tailrec, then maybe they would change the code and they would make it not be tailrec anymore. And then it would work when they test, but when it goes out in the field and the numbers get big, then it would crash. Whereas if you say tailrec, I am explicitly saying that this function is intended to be tailrec, and so that the future programmer that comes after me can see they mustn't break the tailrec. This function needs to stay tailrec. And then also the IDE can warn you, because if you now change this and you put the Fibonacci in a different place, the IDE will tell you this is not a tail recursive function anymore. Some pros and cons. So functional, like if you've got functions that work on data and transform them, they're really, really good for like big streams of data that you want to transform from one thing to another. A stream of data where you don't know how big the data structure is, it's like a feed, it's like a Twitter feed, or it's like a big stream of data. So they're really useful for that. They are good if you want to extract pieces of an algorithm, if you want to extract pieces of functionality and little pieces of the algorithm into little functions, and then you can split things out in either lambdas or little functions. And they're really, really good for testing, because if you're writing these small pure functions and you know they're pure, you can test these functions in isolation and make sure they work 100% of the time. The other thing is because you're not changing the data, because the functions are pure and you're not changing data on the outside, you can have multiple of these functions running because you won't have a concurrency issue, because you won't have a global state that you're trying to modify. And if you're running in multiple threads, then there's some other concurrency contention with changing the global state. It's super, super compact. There is a flip side. We'll get to the flip side. And then this concept of referential transparency, you can use that to optimize. It's really useful to do memoization like that. Now, some of the cons, let's jump with the red arrow here, is that it's super compact, easy to read, but that means you can write these dense chains of functions that one calls the other, calls the other, calls the other. And then it's quite difficult to read because you have to keep track. Oh, I'm mapping now, and now I'm flat mapping, and now I'm converting something. And sometimes I find that quite difficult to debug. You need to debug that by either making sure the little functions work or by putting some other side effect in those chains. So sometimes that can be quite dense and difficult to debug. You need to learn some other abstractions. So if you want to use functional style in Kotlin standard libraries, you need to learn the Kotlin standard libraries. You need to understand how map works and how flat map works or how filter works. And then, since you're working with immutable objects, you might have an issue with memory allocation. There are ways that can happen, so things can happen lazily, so you don't blow out your memory. But memory could be something that you need to keep into consideration. So now, I don't know how we're going for time. Are we okay for time? I want to take a real-world example. So this is all nice. This is great. This is Kotlin theory. You could read that in the Kotlin documents. But let's look at a real-world example. And the real-world example that I want to take for Android World Wide is an Android app. So an Android app looks something like this. So this is using, say, maybe the latest guidelines of how to write Android apps. We might have some declarative piece here. This could be Jetpack Compose. This could be views. When we're using things inside the Android framework, we're definitely in object-oriented place, because we might have an activity and we might have our activity that's derived from that activity. Or we might have a view model that's derived from a base class view model that gives us certain functionality and certain state. So we're using object orientation there, definitely. We're keeping some state and some behavior in something, say maybe it's a view model, you're keeping some state and behavior, and we're hooking the state and behavior onto our UI, which could be Compose or could be Views XML. Then we might have some other global state. We might have some global state that comes from the network, that comes from the internet. It might be coming from a database. We might have some other repository function that pulls things out of our global state, because our UI needs the global state in a way to be able to show what's happening on the screen. And it might be that the database that's providing this global state provides it in a flow, so that you can consume it in a flow. And when you get it in a flow, you might be using functional style of code to access that flow and to transform that flow so that you can get the data into this state over here so that you can show it on the UI. So what you can see here is that this is just a modern Android app, but we have declarative code. We've got snippets of imperative code sitting inside here. We've got functional code maybe happening. We've got object-oriented code. We've got all of the 4 paradigms in the Android app at the same time. So that's why it's important to be able to understand a little bit of how and why you would use the one paradigm over the other paradigm. And there isn't one, according to me. I'm not a Haskell coder that believes only in functional code. According to me, for these kinds of situations where we're coding in Android, you need to pick the right solution for the problem that you have. If you're working in a place where you've got declarative code, or maybe you're in the Gradle build file, there's some declarative stuff, then you use declarative code. If you're interacting with the Android framework, then you use object-oriented. So it requires me to have a fluency in all of those paradigms. And it means that I can use some of the pros, like these pure functions that are testable. I can use some of the pros of all of the paradigms to make my code more understandable and to make my code easier to test. And in fact, the Kotlin language supports this kind of solution from their basic design principles. And this is a quote by Roman Elizarov. You can read it by yourself, but basically what he's saying is that the language should be able to solve the problems that we as developers face every single day, not try and have a specific paradigm or push a specific paradigm that's maybe uncomfortable for the solutions that we're trying to code. Here are my resources. I will share a link on a subsequent slide, and then you can click and look at all the code and find all of the links for all of the research for this whole talk. And this is just a little bonus snippet. This is the Java code if you decompile the tail recursion function and you look at the Java code. So this is what the compiler turned that tail recursion function into. Now on this slide, you can choose. You can either scan this QR code here and give me some feedback on the talk, or you can go to this link and get the PDF for the whole presentation. Or you can ask me questions afterwards on Twitter, or you can ask questions now in chat if we have time. I think we've got time.
Hi there. Can you hear me, Maya?
Yeah, I can hear you.
Hey there. My name is Ryan. So Kimmy had to run out to do a meeting, so I'm just jumping in to field the questions.
Oh, that's great. That's cool.
Yeah, and sorry for the interruption earlier. I've been using StreamYard for about a year, and I still find its UI a little tricky.
That's the problem. I thought you had a question. And in fact, you did, because you were asking about the monads, right?
Yeah, you ended up. It's kind of a bit of a joke question to ask everyone about functional programming, but you actually covered that in the talk, which was terrific.
Yeah. So I know. I mean, people, if you say functional, people say, "Oh." I had the same reaction.
Absolutely. First off, congratulations. That was a very polished talk, so very well done there.
Thank you.
So if anyone has any questions, go ahead and write them in the comments. I have a couple questions myself, which we can get started with. So the first question I had was, and you kind of addressed this, I think, at a couple points in the talk, but should people start learning functional programming with math, or should they learn it by just writing code, perhaps in a functional or partly functional language, or a bit of both? What's kind of your take on that?
Okay, so I think anybody should learn things that interest them, that excite you. If math excites you and it makes you understand coding better, then I would say learn it by math. If math is dry and you feel you can't get a grip on it, then start coding. Start practicing by learning coding examples. What I was trying to say in this talk is that it's important to understand all of those paradigms, and you were probably using all of them anyway. Maybe you didn't know the words, or you didn't know that you were even using all the different paradigms, but they're there. They're, as you can see, in any Android app. And so, yeah, does that answer your question?
Absolutely, and that's very much in agreement with that. Interest and what works for you is particularly important. You don't have to do it one way or the other. Whatever works for you.
And in fact, sorry, there's another thing that's really interesting. Is like, I've done this before. I was taking part in the Advent of Code, and I would write an answer and get the gold star, and then look at my code and say, this is very imperative. How would I change this? How would I use the standard libraries? And then I would rewrite the example in a more functional way. So that's another way to learn it, is like to write something and then get yourself to think differently. Think of it in a different way, take a different perspective, and then switch, and then see what the benefits are and see which you like better.
Terrific. Another question. So what are there any sort of functional concepts in general which you don't see implemented in Kotlin? And is there anything that's kind of like on your wish list for future iterations of the Kotlin language?
I'm not such a very in-depth functional coder myself. I mean, I'm a bit of a jack of all trades. I kind of pick up everything there. I know currying, as I said earlier in the slides, is not part of the Kotlin language. I also know that there's a big library called Arrow, which is very functional oriented, and they've implemented a ton of the functional concepts, which I haven't possibly even covered. They've got lots of different kinds of monads. They've got the either monad